So there I was, right, typing comments, thinking, oh yes, type, 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 when I could just go live and talk to you straight to the camera. That's a much better way of doing things. Good evening, I hope you can hear me. I hope you're all right out there in YouTube land, Twitch land, Facebook land, Twitter land, all these other places that I'm just steaming my stream into like an annoying pop-up. We're still trying all platforms just for fun. I know I have at least 1.5 dedicated people on Twitch, which is very exciting. And any day that's going to blow up. It's going to blow up. That's where all the kids are. Kids who are interested in this kind of rubbish. So, hi, good evening. I'm Robin. This is another build along with one of those crazy Erica Synth modules. We have been building our modular. This is what we have so far. We have a sequencer, we have a VCO, we have a filter, dual VCA, we have a pair of envelopes and a mixer. So far so good. There's room, I think, for at least 1, 2, 3 more modules, and then our journey will be complete. And that'll be like 10 months. 10 months of doing these bleeding things. So that's very exciting. I am looking forward to finishing it, I have to say, at this point. But I am dedicated to the task of going through each module one at a time, putting the bloody things together, seeing what makes them tick, see if I can cram any more information into my head about how stuff works. And this evening is one of probably perhaps potentially the most interesting. Why is it interesting? Well, because we're going to learn a bit about randomness. We're doing the sample and hold noise, or noise, sample and hold, depending on whether you're reading the front panel or the documentation on the website. But regardless, these two things tend to live together, which is something it took me a long time to understand. I just assumed that S&H was a weird term that just meant randomness. You know, I'd come across it, I think, you know, I first came across it on my DX100 when I was a kid, and what it meant was that it just pumped randomness, random movement into whatever it was you turned it on to. I could be wrong. But once I got into modular, because you see that kind of thing in synthesizers all over the place, and you just dial it in and it does that thing. It does the up and downy kind of stuff. But and you know, and in using that, you would completely ignore what sample and hold was trying to tell you. That term, well, it didn't really mean anything. It's just S&H, sample and hold. Okay, great, that's fine. But what it actually means is that it samples a voltage, or samples a bit of audio, samples something. It takes a measurement of a waveform at a particular time and holds on to that value. That's all it does. And so you can use sample and hold on any kind of source material. It could be, like I discovered, where did I discover this the other day? What was I doing? Was this playing with the Moog Mavis? I was trying to do some sample and holding, and that's right, because in order to create like an illusionary sequence in the non-sequencer Mavis, you use sample and hold, but it samples the oscillator. So if you're using a square wave oscillator, you get like 2 values, because it's either up there or it's down here. And so every time it either samples the top one or the bottom one, and that's all you get. And that took me ages to work out what was going wrong with this. Why am I only getting sort of 2 notes out of this machine? Because it needs a bit more of an interesting waveform to sample. So when we talk about randomness and sample and hold, I'm sure all of this is going to be in our wonderful manual we'll get to in a minute, but heck, I'm talking now, so I'm just going to keep on going. He says, so if you use noise as a sound source, noise is essentially every frequency all jumbled together all at once. So when it samples, it will grab hold of potentially any value at all across the whole range. And so that gives it its maximum amount of randomness. Now, because you are sampling something, sampling a waveform, you can use that to restrict what sample and hold can do. You can use it to essentially reorder a sequence, if you like. Interesting stuff once you know what it is it's supposed to be doing, as opposed to just being randomness. So So this is what we're building today. I have no clue how difficult it is, whether this is a basic circuit or a more interesting circuit. I don't know, but what I can tell you is that I have already measured my resistors. They're all here, look. So that's going to save us like half an hour, which I thought was a great idea. So what we won't need today is this. There's the front panel and PCB. Doesn't look too complex. Put those to one side for tomorrow night when we'll do the soldering, all being well. Today, we're looking at putting it out on a breadboard so that we can slowly gather what on earth it is all about. That is the plan. Following Moritz Klein's hopefully excellent manual, which will tell us all about it. Now, I'm just going to have a slurp of coffee. You can hear me all right, can you? Hi, Jim. Jim, is that you of Infinite Machinery out there? Well done. I just need to open my door because I'm actually really starting to get warm in here. And I don't want to have a fan on. It is a bit cooler generally, so hopefully I'll keep the air moving. Right, so yeah, you're very welcome to just tune in and watch the agony of me trying to understand concepts in electronics. You're very welcome to build along or watch this at another date when you have the kit and put it together. These are available from Thonk, from Erica Synths, and from Perfect Circuit, I think, and all over the place. And of course, this video will be available on my YouTube channel, along with all the other videos of building all these modules for forever. I think YouTube's forever, isn't it? I think it is. Oh, I don't want to mix those up. So, yeah, thanks for stopping by. Good to see you. Lots of familiar names in there. Thanks, Ian. Mic is a bit low. It always is. Turn it up. I mean, the microphone is literally here. You can see it. Now, if I was doing a live stream with Sonic State or something, I would have it here. But I can't do anything. I can't turn it up. It just is what it is. So, you know, you're going to have to turn it up at your end. I don't plan on swearing, Ken, but you know how this can go. But, I mean... But this is how I always have it for all of these videos, and you know, when I look back on them, they seem all right. So as I say, you know, turn your telly up or something. I will speak as clearly and loudly as I can. Excuse me. Hey, while you're waiting, buy yourself a really nice mug. Link is in the thing. Okay, so what are we doing? Let me do something. Let's have a look at the overhead. I think that one. Let's have a look. This will get smoother as we go. Just checking that you can see everything. So here, down here, is all the resistors. So what we'll do is we'll go through the bill of materials. So this is the manual. The manual you can get direct from Erica Synths website. Let's just rewind a little bit before we get too far. So Moritz has said at the beginning of this one, weather. That's an interesting spelling of the word weather, but let's go with it. Whether you use it for self-sequencing or adding a dash of randomness to your filter movements or for rough analog bit crushing. I've never quite worked that one out, I have to say, but you know. A sample and hold circuit can often be the secret sauce that makes a patch distinctive. Yeah. So he's come up with a super simple JFET based implementation. Then upgraded it with a couple of extras like an internal clock. Cool. And a dedicated slew. Now I think you could probably do a whole other video on slew. Slew is one of those mysterious concepts. It's like, what? Do you mean glide? Do you mean an envelope? Do you mean portamento? No, we mean slew. Do you mean slow? No, slew. So, oh, I don't know. It's one of those strange terms, but apparently we've got a dedicated one, so that's nice. My soldering live streams do go on for hours, guaranteed. Yes, they do. So do these ones, for that matter. So, the first thing we've got is a circuit diagram. Let me bring that up for you, so you can see that a bit closer. I'm not seeing what I need to see. Oh, I can see it there. Whoa, look at that, fantastic. I just saw my own magical zoom, and that was very exciting. So, yes, here's our circuit diagram. At the moment, it's not telling us a whole lot because we don't understand what on earth is going on. But we do have, certainly I can see, let me put my mouse on it, signal input over here. It's going through, there must be an attenuator on it in order to change its input coming in. Oh, look, there's a bit of a transistor thing there, going through an op-amp. There's another op-amp with a regular feedback thing there going to the S&H output. So something must be going into that. And this over here, we have a slew output with a slew in. Signal in. Ah, of course, but your signal in isn't going to be something you're using, isn't going to be your your baseline or whatever. That's just going to be whatever it is it's sampling, presumably. Right, so this is completely complete mystery at this point. Let's keep going. Okay, so a noise generator. So what is that then? That's the sample and hold circuit. And then we've got this noise generator. And that, of course, gives us something interesting to sample. Ah. Instead of just using one noise color, we're going to have two, pink and blue, in addition to the standard white noise. Don't see blue noise very often. And this is the circuit diagram for that. I wonder how it gets made. How do you create noise in a purposeful way? This is what we're going to find out. It seems to have a lot to do with capacitors and resistors going to ground of different values. Interesting. The FET is acting as a switch. See, there's a collection of words you put together and it still doesn't make any sense. Hold on to yourself, Ken. There's some op-amps. Right, bill of materials. So let's just check that we have everything we should have. So let me go back to the overhead. So you can see all this stuff down here. So in my list, I haven't counted whether I've got everything that I should have, but I should have. Let's go through this. Now these don't come labeled, so you can either look them up on the internet, as in look up the color bandings, or you can measure them with a thing like this. You see, this is what I did. I'll put this down here. I put it onto ohms. I mix everything up on my desktop, and then I put this on like I'm charging Frankenstein, and it goes something or other, 47k, I think that is. What did I say it was before? Did I not write on this one? Oh, I found one that I didn't even do. Oh, bleeding heck. Right, let's try this again. So there's me thinking I got ahead. So the survey says 475 meg, 0.475 meg, which is 470k. I'm going to go with, because that's on my list, 470k. Don't want to spend too much time here. 470k. So I should have 1 meg. 1 meg 2, yeah. Let's put those just to that edge of the screen there that you can see. 2 470s, I just did that. Check. 12 100s. Oh. Reg, why are you commenting on my photo in Facebook at this time of night? You should be watching the live stream. I'm going to assume there's about 12 of those. They're the 100k ones. 51k, there should be one. That's a single by itself. So is that, did I not do all this? Oh dear, I obviously missed things. I can finish those off. There's a 51, 47, 47k times 1, 33k times 2, 22k times 1. Is that 22k I wrote on there? Yeah. 20k times 1. Don't think I've got that yet. Stand corrected. Yes, I do. That's a 20k. 10k times 1. That's a 10 ohm. 4k 7 times 2. Yeah. 2k times 1. I've actually got 2 of the 2k's. And the 1k's times 6, I've actually got 5. So I might have to, I do, funnily enough, Simon, hi, you're on Facebook, you crazy man. That's where the extra hip hipsters hang out, because there's nobody else there. So you can do what you like, and you know, and fill the entire space. What have I got? Yeah, 5 of these. 5 of these when there should be 6. But as I say, I have, funnily enough, I've got 2 kits of the noise and sample and hold, so I can always go and fish another one out if I seem to be missing one. It is worth checking through this when you receive your kit, just in case there's something wrong, and then you can make inquiries with where you got it from. 1680, that's that one, and 2 10s. So I've got a couple here just to finish off. You have the right number of 1k and 2k. Oh really? So apparently the 1, 2 and 2k's, that should be right. So there should be 2 2k's and there should be 5 of the 1k's. Good. Okay, thank you for that. That's much appreciated. It will probably, you know, show itself in the actual building out of the thing that we do. So this one is 10k, 10k, yeah. That's 10k. And this final one, 100k. Is that right? Was I missing anything out? Oh, I forget now. No, it's a 10k that I was missing. Everything else I've got. This is another 100k. Okay, so that goes in my pile of 100k's. Right, good. Done that bit. We can move on to the action-packed stuff, I think. So, bunch of capacitors. Oh yeah, we didn't try those yet. So let's have a look. Oh dear. It's important to do this. If I don't do this, I then get confused. So this is always helpful because it shows to me what the components are. So when I'm looking for them, eventually it all makes some kind of sense. You have to do the work. That's the question. You just might need a magnifying glass to do it. So there should be 3 of one thing. Electrolytic. Oh, that'll be these, fellas. That'll be these, right. 47 nanofarads, picofarads, microfarads. 47. Yeah, those are the same. Okay, check on the capacitors, electrolytics of those type. Oh, they're all just stuck themselves to my microphone. There's a foil one, a 1 micro foil. Is that going to look different? There's 2 of them, so it could be these. 680. Those are the, that's something else. 2N2s. Oh, that's something else. J63s. J63s. Look at that. J63s. 2 of those. Yeah, check. ohms over there. 470. Could that be? No, that's a ceramic. So 470, one of 47K63. Yes, one of those. 8 of the 104s, which are these little weenie buggers. 104s, yeah. 1, 2, 3, 4, 5, 6, 7, 8. I hope you're all doing yours at home. J100, yeah, that's that fella. And 2, 5, 6, something or others. That must be these. No, I already said that wasn't those. Oh, it'll be these weird blue ones. These blue ones here. 5N6J. Yeah, yeah. Good, good. Then 2 of the 2N2s. Yeah, that's those two. 1 lone ceramic. A 102. Good. And these are 680 picofarads. Great. Lovely job. There's some diodes. The big fat power regulator ones, and then the little weenie ones that actually do the dioding business in the circuit. A couple of transistors, or 3. Of course, one of these is the famous JFET. I've got a, I don't know what that is. N21? No, there doesn't seem to be one. This one. What am I looking for? 548. That's a 548. That's a 3904. So this 113, yeah, that's the JFET. Okay, good. Couple of pots. Got a bag of bits here. 2 pots in. Oh, there should be 3 in total. Yeah, 3, 1 different. Yeah. An LED. Yeah, I've seen that. Bunch of jack sockets. Oh, I think I stole some of the jack sockets, so I'll have to steal some from somewhere else, but that's no problem. In fact, I have a bag of the things somewhere. I'll steal those from somewhere. 8 of them, really? Well, I did stole a lot. Do I have 8? Anywhere else? Yeah. No, I certainly do not. Okay, I'll have to find the my bag of those. I wonder where they are. I'm sure they will present themselves when they become needed. I mean, we only need one for the output, don't we? Possibly. Oh, there's all sorts. There's all sorts. A couple of chips. Oh yeah, chips. A couple of chips there. 2 of those, 1 of those. Right, so now we're back to the old breadboard. Our friend, the breadboard. Now, I go through this every time because I can never remember it, and it's important. So, the layout of my breadboard is backwards to what's in the manual. That's just how it is. I've had to learn to live with it. There's nothing I can really do with it. Whichever way I turn it, it ends up backwards in one way or another. So what seems to work best for me is kind of ignoring the positives and negatives on this side here, and just know what it is that they're all plugged to, and absolutely follow the manual for what is positive and what is negative, what is +9 and what is -9 volts, and what is ground. That's what I do. I ignore the markings on here. Hi Robert, how you doing? Are we on the overhead? Yes, we are. Oh, just checking. There we go. So, seems a bit dull for some reason today, like it's in shadow. But hey, I think we'll cope with it. I think we'll cope. So all these on here are from last time, so I'm going to have to probably pull all of those out, I imagine. But with a bit of luck, I can reuse them. What I will leave in is this line here, which is part of the battery business, which we're going to plug in a moment. I mean, in Eurorack you're using, I don't know what you're using, 12 volt power ultimately, are you? Oh, I don't remember. But anyway, in doing this we're using a pair of square 9 volt batteries which do the business for what we need for this process of testing and working it all out. A pair of 9 volt batteries is enough. So we don't need to get hung up on the power. So for power, a pair of 9 volt batteries, cheap as chips, sort of thing. Put their hats on. Like so. Then, following our diagram, we need to go positive from one battery. Let's go from here. So positive from one battery goes into this inside tract. Even though it says negative, I'm going on the inside tract. Then the negative, which is attached on this battery to ground, goes to the outside track. Is that what I did? No, I completely didn't. All right, I've blown the battery. Right, okay, that outside track like that. With the other battery, the positive is also connected to ground, and that is the inside track on this other side. And I've connected them together with this long wire. And then the negative on this side is the minus 9 volts, and that goes on the outside. So if you're looking at this, I think I've got this right. Let's hope that I have. I don't think, yes I have. I've got it, I've definitely got it right. You've got positives on the inside, negatives on the outside, and the outside negative is patched to that inside positive. And that gives us ground on this first line, and ground on that top line. So if you see these two rows as a pair, you've got negative 9 volts, you've got ground. Then you've got positive 9 volts and ground. Good, I think that's right. And then as we put our components in, that's all just going to flip in work. Yeah? Glorious. So, sample and hold basics. Right, let's have a go at this then. Are we ready? Are we all warmed up? So I'm not doing anything on the breadboard for a while, so let's go back to the manual and we'll go through this bit together to see if we can work some of this out. So, although the name is intimidating, can you see all of that? I've not covered anything up. No, that's good. It's actually quite straightforward. Hooray! Before we can start with that though, we need to make sure we understand what it does. Well, kinda. So name is quite helpful. At its core, a sample and hold does two things. It samples and then it holds a voltage. Okay, so we've got a signal. We seem to have a 5 volt and a 0 volt. There's a blip there which is triggering the sampling of that signal, and the output you get is the thing there with the thing out the holding end. See that? God, this is going to be easy. So you've got two inputs. One that gets the to be sampled voltage, so another is your source, let's call it, and the other one is a trigger which makes the sampling happen, like you're hitting the record button on your MPC. Got it? Oh, Ken, you're funny. At the output, the circuit should then provide a copy of the sampled voltage until the next trigger comes, so it holds it until the next trigger. Makes sense. If it's too abstract, no, we get it. So, yeah, so interestingly, you can stick in a nice wave like that and it will sample and hold and make it stepped. Yeah, good. The output then looks like a repeating set of stairs, so instead of a continuous slope, we get a kind of digital approximation. Yeah, this is exactly how analog to digital conversion works, I suppose. If you do this with white noise instead of a straightforward waveform, you get a weird random voltage at the output instead. Yeah, and we love that, which is this thing here. We love it. It's one of my favourite things. And while implementing this might seem like a tough job, at its core it's very simple. Great. So, we only need two elements, some sort of switch and a capacitor. Note 5. Oh, that's going to say what's it saying? Note 5. Note 5. Read more about capacitors. Okay, great. So here we go. So start out simple. Let's take a look at our most naive. Naive? Is that the right term? What are we being naive about? Because like naive is like is always used in a disparaging way. It's not a compliment. I wouldn't even say that it was a, well, I don't know, I suppose it is. So we're being naive, we're being simpletons and unschooled about this implementation, using an actual manual momentary switch. Yes, here's how it works. We apply our to be sampled voltage to the switch while connecting the other end to a capacitor. Before we push down on the button, the capacitor will be empty, so the voltage on the right is going to be 0. Yes, as soon as you push the button, the current will flow through the switch and into the capacitor, charging it up. Same goes in reverse for a negative input voltage. Once the voltages on both sides are equal, the current will stop. We've sampled the input. Yeah, I mean, I'm sounding all really cheerful at the moment because at the moment I understand everything. It's going to get bad later and I'm going to be banging my head against the walls and getting aggravated. But at the moment, this is all good. I like this. Except my question would be, isn't there time involved in filling up a capacitor? Is that important? And then how do you stop it releasing? Now, if we release the button, the voltage on the right will stay exactly the same no matter what happens on the left, because we've cut the connection. Oh, all right then. Cut the connection, so it can't flow out. I suppose, going with it, why doesn't it just fall out of the hole? This is a liquid after all, isn't it? Aren't we talking about things in terms of liquids? And so therefore you've filled up this bucket of a capacitor. And now that you've stopped doing it, why doesn't it just drain away? Anyway, the only trouble is that we're not interested in manual control. Instead, we want to trigger electronically. So you have to exchange a push button for a different type of component. Good, yeah, this is good. This is good. Switch versus a bacon sandwich. So if you now already thinking about transistors, you're on the right track. Oh, I wasn't. Were you thinking about transistors? I wasn't thinking about transistors. Transistors, as we know, are often used as electrically controlled switches, of course. In this series of kits, we've exclusively focused on a specific type of transistor, the BJT, or bipolar junction transistor. This type of transistor isn't ideal for our purposes here for a whole bunch of intertwined reasons. Don't want to go into too much detail, so we'll heavily simplify the issue. Let's assume we directly replace our momentary switch with a BJT. So, free flow, capacitor, yeah, sample. Weird flow, apparently. Oh my goodness, it doesn't know what it's doing at the base of its thingy, and it can go either way. So there's no clue as to what's going out. Okay. So the transistor will allow the current to flow between its collector and emitter if we apply a voltage to the base. You might think then that applying a voltage to the base is the same as pushing the button. The only trouble with that is that it's not totally true. A closed switch behaves exactly like a piece of wire. The BJT does not. The closed switch will allow for current to freely flow in both directions, depending only on the voltage applied across it. The transistor, on the other hand, is much more complicated. The amount of current allowed to flow between the collector and emitter is fixed and depends on a multitude of factors. The amount of current flowing into the base, the overall direction of flow, the transistor's gain level, and so on. Worse yet, if there's not enough current flowing on the main path, the transistor will allow for large currents to flow into the base and fill the gap. Good Lord! So where pushing the momentary switch reliably and instantaneously charges or discharges our capacitor, the BJT will behave much more inconsistently. All right, well, we'll believe you. So it's just sloppy. Gotcha. So instead, we're going to use a different type of transistor called a JFET, which is something that we tend to come across in like distortion circuits. It's better suited to our use case. The junction field effect transistor. What's that? Oh, that's what JFET stands for. Junction field effect transistor. You know, I've never known what that stands for. I don't ask those sorts of questions in case I get an answer that I don't really appreciate. There's two variants of these called the N channel and the P channel, which can either be symmetrical or asymmetrical. To keep things manageable, we'll focus on just one, the symmetrical N channel version. All right. So whenever I say JFET from now on, he's talking about the N channel one. The main difference is that the JFET behaves like a weak resistor, meaning that it allows for current to flow through it depending on the voltage applied across it, no matter the direction. Okay. There are a few caveats, which I'll talk about in a minute. Before that, let's clear up the basics. Good, basics like that. Base, collector, emitter. Base in the middle, collector, emitter. Yeah, it works actually. The physicality of it does match the circuit diagram, which I find enormously helpful. Gate, drain, source. Oh, well, I don't know which ones these are. I don't know what these... Okay. So the JFET is on the right. The BJT is on the left. I think that's correct. Yes, because we know that the JFET was the J113, don't we? Okay. So instead of a collector, base and emitter, like we have on the left here, the JFET has a drain, gate and a source terminal. The flow of current between drain and source is controlled by a voltage applied to the gate. All right. Since voltages are always relative, though, we have to ask what the point of reference for that gate voltage actually is. Answer is simple. The point of reference is the source terminal. So when we're talking about the gate voltage, we're talking about the voltage between gate and source. Oh, the long answer is a tiny bit trickier though. Great. As I said, the direction of flow between drain and source can be reversed freely. And if we think of a source as the terminal that the current is flowing out of, then source and drain basically switch positions once we do reverse the current flow. Okay, so effectively the gate voltage is always measured in relation to the terminal that the current is flowing out of. And that will always be the one where the applied voltage is lower. See, already my brain's starting to hurt now because we're getting into that whole area of what is voltage and what does it mean and what's that to do with current and how that actually functions. Anyway, we'll keep going. Read more about it. Yeah, read more about resistors, that's fine. So, let's keep going. With that in mind, here's how the gate voltage relates to the drain to source circuit. For this, we're assuming that the drain and source voltages are fixed at 1 volt and 0 volt respectively. So the drain and source are 1 volt and 0 volt. So we're talking about drain to source current. But surely the source would have to be a voltage, wouldn't it? As opposed to nothing. Oh well. Now generally the JFET is considered to be fully active when there's no voltage between the gate and the source, meaning that they'd both have to be sitting at ground. I thought you needed a voltage to open the gate. Then the transistor will act basically like a very weak resistor, and so Ohm's law applies, which tells us that the amount of current flowing is determined by the voltage between the drain and source fighting the JFET's resistance. Yeah, V equals IR, so I equals V over R, voltage divided by resistance. if we push the gate voltage up from there, we can increase the drain to source current further. Yes, this happens because we are further decreasing the resistance. But beware, if you push it up too far, a large current will begin flowing, potentially destroying the thing. Now, if we pull the gate voltage below the source, we can reduce the amount of drain to source current. This happens because we're increasing the JFET's resistance. It's kind of like, you know, I mean, one of the... it's like there's a certain amount of mysticism involved, I feel, when we're talking about voltages, currents and resistance. I mean, that should be the basis, you know, the basis of most electronics. It should be something that I should completely and utterly understand. And yet when I read this and go through it, it just, the usage of these terms and the interplay between these terms just doesn't make sense to me. I don't know why that is. Why can't I fully envisage what this is all about? Because when it says something like, if we pull the gate voltage below the source, so if we change the voltage, we can reduce the amount of drain to source current. But this happens because we're increasing the JFET's resistance. So why don't we say, if we increase the JFET's resistance, we can reduce the amount of drain to source current? Because that makes sense. Increasing resistance, reducing current, that makes sense. And then a byproduct of that is that the voltage goes below the source. I mean, that makes far more sense to me than saying pull the gate voltage below the source to reduce the current. And this happens because we're increasing the resistance. Do you see what I mean? Am I speaking any kind of sense? I mean, what I've learned through these sessions is that Moritz does his best to simplify things, and so I'm kind of grappling with that simplification. At the same time, my brain is trying to reconcile that with perhaps some other bit of knowledge I might have somewhere, and it sometimes gets into a bit of a knot. But consistently, Moritz is right about what he's saying, and the attempts I make to grasp it tend to be just slightly mistaken. Do you know what I mean? Maybe you don't. Who knows? Who knows? Who knows? Is that all still flowing through? Yeah, something's going on over there. Anyway, let's continue to focus. As we know, a steady voltage faced with an increasing resistance results in a decreasing current. Sure. Once we exceed a voltage difference of more than 4 volts, JFET turns off completely to prevent any current from flowing. So in short, via the gate to source voltage, we can vary the resistance between drain and source from very weak to almost infinite. Okay. What are we trying to achieve at this point? Does anybody know? Let me know in the comments what it is we're trying to achieve. Now you might have noticed that the drain to source voltage in our example is suspiciously low. I did that because the resistor comparison only really holds up for relatively small voltages. Let's look at a different graph with bigger voltages. Stop that. That's milliamps. Here you can see the relation between drain to source voltage and drain to source current. If the gate to source voltage stays at 0, so source and gate are fixed at 0, while we push up the drain voltage, oh dear, we can see the relation between drain to source and voltage, drain to source voltage and drain to source current. Current going that way, voltage going that way. As voltage increases, current increases. drain. Is this what are we seeing in this? Is this source? Oh, gee whiz. Interestingly and annoyingly, the JFET stops behaving like a resistor after we increase the drain voltage beyond approximately 3. So this is drain voltage. Beyond 3, it stops then and becomes a straight line. Because with a resistor, the current will simply keep increasing. With our JFET, we run into an upper threshold. Okay. This threshold, along with the general relation between gate voltage and drain current, can vary quite heavily depending on the JFET model you're looking at. So it's just kind of a rough average. Let's try this out. Look, we've got a trying out thing. Let's go and have a look. See whether this can shine any light on what we're trying to understand. So, have you still got that up? Yeah. So JFET behavior. Adjust me via the sidebar. So this is the gate voltage. And this up here is the source, voltage source. And this is ground. So this is gate voltage. If I pull this down, reduces in amps till we get to -4, where it should cut off completely, more or less. If we bring that up to +1, it's really steaming. If we increase the drain voltage, it goes up and then it flattens out. So I can appreciate what appears to be working. That's something at least, yeah? Is anybody out there? I get worried when there's been no comments for like 10 minutes. Anyway, keep going. Switch versus JFET. So, we've learned a little bit about JFETs, I think, or at least a little bit about what's going on. The fact that the drain current is capped is not ideal, but it's also not the end of the world. All it means is that the bigger the drain to source voltage is, the slower our capacitor will be charged up. Alright then. To get the voltage above the capacitor up to 5 volts, a specific amount of current has to flow into it. With our switch, this happens almost instantaneously, since there's barely any resistance, and certainly no speed limit. With our JFET, it will take a short while, precisely because it has a speed limit. Now, JFET, it will take a short while because it has a speed limit. Thanks, Jim, that's appreciated. So, instant charging because of the piece of wire. Instant charging there also. It's 100 milliseconds of charging. Slightly more when it's 10 volts. You don't quite get the right stuff out. So if we double the input voltage, twice the amount of current has to flow into our capacitor. With our switch, it's almost instantaneous. With the JFET, though, it takes almost twice as long. Why is this a problem? Well, it has to do with the accuracy of the sampling process. If we're trying to sample white noise, the voltage is jumping around wildly and randomly. With our momentary switch, the voltage we sample will always be accurate and true to the input. But it doesn't matter, does it? Because it's white noise. So it's not as if you're going to choose anything. It's supposed to be random, and so the fact that it's late, I can't see how that makes any odds at all, because you're not expecting a particular value. It could be any value, so it still could be any value. Wouldn't it? So what was I saying? So with our momentary switch, the voltage we sample will always be accurate, because while we press down on the button, the capacitor voltage will precisely follow the input voltage, as the charging process is instantaneous, and once we let go, then it will hold that value. With the JFET, things work differently. First, instead of pushing and releasing a button, we have to bring the gate up to the source voltage, and then pull it down to a really negative value to make sure it will always at least be 4 volts below the source in order to sort of turn it off, or essentially that's turning it off, isn't it? Second, while we do that, the capacitor voltage will be lagging behind the input voltage during big jumps because the JFET's maximum current cap. So this diagram here is showing our instantaneous sample, and here it's showing our grabbing at it, and oh look, our sample voltage is actually much later. So if we activate the JFET in the middle and then deactivate it on the right, so activated, deactivated, the capacitor voltage won't be equal to the then current input voltage, simply because there wasn't enough time to get it charged up to that value. Instead we're getting an output that's somewhat lower. Alright, this is interesting. Why doesn't someone invent a component that doesn't do that? What can we do about this? Well, there's at least 2 things. First, we can reduce the volume of our input voltage, because the JFET speed limit only kicks in if the drain to source voltage is more than about 3 volts. So if we'd scale our input down to 3 volts, and we could charge and discharge our capacitor without the speed limit. Alright, which should increase our sampling accuracy. Great. The only pain point is that we'll also have to amplify the output signal to get it back to the original signal's input volume, original input signal's volume. Second option is a lot simpler. Well, let's do that then. But it comes with a trade-off. Damn it! We can use a very small capacitor. This helps because the smaller capacitor is charged more quickly. Makes sense. Meaning that we'll have to funnel a smaller amount of current through our JFET to get the capacitor voltage up to the input level. This makes the speed limit less of a deciding factor, which in turn increases our sampling accuracy. Downside comes from the fact that every capacitor leaks. No one told me capacitors leak. Really? After all that? Ian, you're dead right, yes, because if you're sampling white noise, what I said is true, because I always speak the truth. Whereas if you're sampling something else, then it does need to be accurate. Yeah, all right, fair enough, fair enough. So yeah, there you go. You see, I'm learning. I'm being taught, being schooled by the good people in the chat. It's not frustration. No, I'm trying. It's just the way my brain is trying to cope with it. It then affects my mode of speech. We're reasoning things out. It's not frustration, not quite. I'll have another word for it. Okay. So even when there's seemingly no way for the charge to leave the cap, it will always do so. Damn it! There's always a droop. Good Lord. Dear, oh dear. To try to avoid this, we can use capacitor types that are described as being low leak. Cool, yeah, but these will still leak. Real things are never ideal. Even our JFET will let I mean, it's all a disaster. As our capacitor loses its charge, the voltage will change. This is sometimes called droop, and it means that our circuit's output is not going to be steady during the hold phase. Right. Now, what's the betting, right, that we're going to use some kind of op-amp shenanigans to buffer the initial value. See, that's my prediction at this point, and that shows how much learning I've achieved during this whole thing. So why is it worse with small ones? Well, they hold less charge, and if the leakage is the same, then it's essentially more. So it's proportional to the capacitance. They lose less charge per second. If we want to increase the sampling accuracy, we're going to have to decrease the capacitor size. But if we decrease the capacitor size, we'll get more droop. Now, after talking about so much about accuracy, you might be somewhat annoyed to hear that in a sample and hold circuit meant for use in synthesizer, accuracy is really not all that important. See, that's what I said. That's what I said, Ian. You corrected me. And I know I corrected myself. At least not important enough to risk a noticeable droop. Because if you're simply trying to sample some white noise, this is exactly what I said, man, then it doesn't really matter, does it? It'll be just as random. This is not to say that high accuracy is never necessary. If you want to sample a tuned sequence to your VCO, for example, you need absolute precision. Otherwise, it would sound way out of tune. But that's a very specific use case, and I think we can neglect for our very basic implementation. He's just dismissing your idea. He's just throwing it out. He's just going, no, that doesn't matter. This is fascinating. Fighting talk. So, okay, so here we're getting to the nuts and bollocks of it all. Sorry. Sorry, Ken, swear jar. Thank you. And we're going to get down to a bit of breadboarding in a minute. That's great. Let's get to that. Let's get to that because it's already been an hour. So, this is our core thing. I've got a signal coming in. Got a funny square JFET thing transistor with no arrow because it's not really a transistor, it's a JFET. That's got a 1 meg thing tied from there to there. And this has got plus and minus 12 through a diode. So it only goes in one direction. So there's a voltage being created here. It's got a sink capacitor. This is a capacitor we're trying to fill. And then we've got this fella here with the held voltage. So here's how I decided to set it up. For now, the input signal is going straight into the JFET. On the other side, I've settled for a 100 nanofarad capacitor, big enough to avoid obvious droop. After the capacitor, I've placed a simple op-amp buffer. This is necessary because we need to isolate the capacitor as much as possible to keep the charge inside it steady. And with a buffer, we can provide a copy of the voltage level above the capacitor to be used by other modules without pulling any current from it. The 1K resistor between the buffer and the output protects the op-amp from short circuits. See? So far, so simple. But what's up with the resistor and the diode at the JFET's gate? Well, as we know, we need to bring the gate up to the source voltage when we want the JFET to conduct, and then put it down when we want it to block. I understand that bit now. The problem with that is that depending on which way the current is flowing, source and drain are switching positions. Oh yeah. So whenever the input voltage is higher than the voltage at the capacitor, the right-hand terminal will be the source. But once the situation reverses, the left-hand terminal becomes the source. So strictly speaking, we would always need to monitor the voltage levels at both terminals and then apply which is lower to the gate. Although this is doable, there's a way simpler way, dirtier solution, connecting the input to the gate via a very strong resistor. So whenever the input is lower than the capacitor voltage, everything is fine. Gate and source voltage are identical. But if the input is higher than the capacitor voltage, we run into trouble, right? Because now the gate might sit significantly above the source. And in that situation, we'll get a large current flowing into the gate. It might destroy it. That would be true if it weren't for the huge 1 meg resistor severely limiting that current. Because of this, we'll never see more than a few microamps going into the gate, which it can easily handle. Better yet, the microamps flowing into the gate will make the gate voltage drop to a value slightly above the source voltage, because it's a simple diode. So as long as the voltage at the top is 0 or below, the diode is blocking. As soon as it goes positive, it will start to conduct. Yeah, because if it's 0 or below, it's trying to come back the other way. So, simplified, the more we push from above, the quicker and wider the diode will open, sinking most of the current we manage to squeeze through that ginormous resistor. It's as if there's a weird little trap door at the bottom that opens further the more you push against it. Because of this, no substantial voltage can build up above the one at the source. We'll get a couple of 100 microvolts, yes, but that's it. So with this setup, the gate voltage will always be at or close to the source voltage, as long as the diode below the gate doesn't conduct. So it's there to activate and deactivate the JFET. Whenever we want to start the sampling process, we push the voltage at the bottom up to the highest level we have. That's 12 volts. In a Eurorack system, we've got 9 volts here. then the diode will block because we're pushing the trapdoor shut from below, going up there, leaving the gate voltage at or near the source, thereby activating the JFET. So when the source here and the gate are the same, it activates. So when we push against that, we close it, reducing this to 0. If this is 0 volts, that activates. Once we want to enter the hold phase, we simply put the voltage to the lowest level we have, which is -12. That way, we sink all of the current coming down, so it all comes pouring through that. Get out of it. And that drags the gate voltage down to close to -12, which shuts it off in the process. So let's try this. Yes, I think I really want to try it, to try to really get my head around it. For the op-amp, we'll be using a TL74, which is 4 op-amps in a single chip. Make sure we set it up as shown here. If we reverse power connections, it will heat up and die. Right, so still got this as ground. Left this connected the whole time. It's probably all just ground positive, ground negative. Right, so let's go back to the overhead. Ian, I don't think that's of any use to us whatsoever. But thank you. Thank you nonetheless. So here we go, a bit of breadboarding then for you. This is what we're here for. This is the action. So what we are doing is, let's start off with our op-amp. We've got a whole load of these. I'm going to have to put my glasses on, see what I'm doing. Is this, move that so I can see it. Those are the same, TL074. Yeah, lovely. Going to get my special squashy tool. Just sort those legs out. And while I'm here, I'm just going to take the red ones out so I'm not doing anything bad. So this needs to hit on line 15 and one behind. It's going to be this way around, so essentially upside down. So it needs to go on one below 15 there, up to 20. Is that right? Yeah. Okay, cool. This squeezes in there. So this contains a bunch of op-amps. That's super. Exactly where they are in there, no one ever knows, but it all works itself out in the end. I'm going to need a couple of sockets, so I'm going to have to go socket fishing. Like I say, I have these somewhere. Where do I have them? Load of capacitors, look at that. You acquire these things, I think, once you start doing stuff. See, there's a whole bunch of knobs. Oh, is that them? Well, these are the wrong one. These are the wrong ones, aren't they? See, I got a whole bag of wrong ones. So I'm probably never going to end up never ever using. So where are the good ones? Or maybe they are. Oh no, there's the Cosmo stuff now. Now I'm getting confused. Oh, hey, here we go, in this box. There we go. This is the stuff. Right, get rid of those for the minute. Right. Right, so just a load of those for the minute. Over there. This is it. Right, so we have a socket, we have two sockets, but we start off with a socket over here that's on one before line 10 and up against the side. One before line 10, one after line 10 is what I mean. Like that, so it's on 10 and past 10. Yeah, good. All right, good. So then I need something which is going to go from the back to one ahead of it. Back to one ahead. I need something slightly longer. Okay, I've got a little one which is going to take this to ground, so that front pin needs to go to ground on a nice little blue one. That pin there. Come on, come on. Everybody told me how great it is to have these little patch wires rather than the big dangly wires I used to have, and it is true, it does look more straightforward on the video, but putting them in is a bit of a pain. Okay, all right, so that's going to ground. Got that? You with me? There's a funny wire in there. What's that? A couple of funny things in there. Don't know what that is. Alright, keep going. So I've got another blue one along the top here, which goes at pin 17 to positive. 15, 16, 17 to positive. Then I need a long one. Too long. Not quite long enough. Brown one it is then. So one of these brown ones is going to go from next to pin at the front of that, and it's going to go across. I can't quite see exactly how far that goes across. 1, 2, 3. 3 from the front of that. On the third one. 1, 2, 3 on the third one. 1, 2, 3 in there, I think. Okay. Then I've got a slightly longer one here, which goes from 17 to the bottom. Got a weenie wire. Goes between these two end ones. I've got a diode, which will be one of these. Now you can see the line is going to be that way around. And this just seems to be jumping across the gap next to the op amps. Like that. There's a weird thing on there. I don't know what that is. Hey Arthur from Boston, how you doing? Good to see you. Do you know what that is? Where's my mouse gone? What is that? What is that? Anyway, keep at it. Keep at it. So the JFET, need to find that. The 113, that seems to be up this way round. That seems to be taking a leg from there, there and there. That way round, according to the picture. I need a 1 meg resistor there. Resistor, and that is going between the diode, yep, and it goes to that one of those pins on the JFET. That makes sense. So that's like our feedback loop. So this is going to have to connect. Yeah, well, that first one is on that, isn't it? It's going from that side to that side. That seems plausible. I think there's a right. So I need a 100 nanometer one of these. How do I know what that one is? 100 nanometer. Capacitor. Right, I have to go back up to the bit of materials. Up here. 100 nanofarad is either a 104 foil or no, it's either a 104 ceramic or it's a J100 foil. Now, generally speaking, we've used foils in the circuits. What's it got to be? J100. How many are they going to be? Just the one. J100. So let's use this, shall we? So it looks like a square one in the diagram. Any consensus on that? Oh, gone far too far. Oh my goodness, that's going to get complicated. There's no way we're going to get that done today. Look at the way things are going so far. Just getting, Lord, getting through the basics. Flipping Nora. Okay, back to here. So let's just try to focus. Don't know why I'm telling you to focus. It's me being the idiot trying to do this thing. Right. So this goes one leg off into the middle leg. So obviously the middle leg, I don't know, I need to have a look at, I don't know what legs are which. That goes to there, needs to go one past, goes to the middle leg and one past. It's not going in, come on. Okay. That's in. There's a wire going to ground. From that leg. To ground. Good. So I've got the little one in, got the 1 meg. There's another line in there, which is from pin 3 to that capacitor. 1, 2, 3, Perfect. Capacitor and center. I think that's all done. There's a real big wire, which is a bit unexpected. Okay, 1K, 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 2K, 1K. So 1K goes not on that leg, goes one leg past and to the back of another socket. Let's put this socket in, which is 2 away from there. There's a gap of 2. That. So this goes again 1 away to the back of that. Don't know why I'm whispering. There, good. Now I need something to jump. Do I jump with greys? Or do I jump with blues? Jump with blues. It's jumping over there to go to ground. And that goes from there to ground. That goes to the entrance. There's nothing else going on. Okay. So if I what's the worst that can happen, Ken? Are you nuts? So just having a look at this for me, if you would. I have this thing here, like some kind of donut. Don't know what that is. What is that? Is that an LED? I don't know. I don't know what that is. And then also I've got this big thick thing here, which I guess is just a wire. It's just remarkably different. You know, remarkably different enough for me to go, what the heck is that? So I can take one of my regular patch wires and plug that in. So that's the end of the one. And that comes in to pin one on there, the other side of the JFET. I guess that's what that is. But I do not know what that is. Don't know what that is there. What is that? Anyway, let's just pull away for a moment and let's see if, let's just go to the next one and see if that changes. Does that disappear? That looks like a wire. They're just wires. Those are just wires. Let's go with that. No, there's nothing there that looks like it. I don't know what that is. We have a weird thing going on. See the description below? Alright, okay. To see if everything works, connect a slow oscillation, like from a looped envelope, as your to-be sampled signal. Next, hook up a jumper, okay, to the diode at the marked spot. This way you can easily trigger the sample. Okay, thank you. Thank you. I appreciate that. I would have got to that. I would have done. I would have got to that. Next, connect this output to the multimeter. So there's certain things I'm going to have to do now. I'm going to have to get my rig here to use this as a source of something. Ow! It's actually plugged in to something. Okay. So I've got this up here. Yeah, you'll see that going on. Good. Magic smoke, not worried about that. So to see if everything works, expect a slow oscillation. So from a looped envelope, is that what that is? There's a loop. There's a looping envelope. Why not I use an? I don't have an LFO. So I've got a cable here. I'm going to need something longer than that. Is that one longer? Yeah, let's use this one. Oh, ow! Sorry. Excuse me. Take that out of there. So, envelope out. That is plugging in. I've got 2 sockets. And I need another jumper, as suggested. There we go, which is on the end of the diode there. So, see if everything works as expected. Connect a slow oscillation. Next, hook up the jumper to the diode at the marked spot. So, left one you reckon is the input. That seems right. That seems right, because that's the one that's connected to the 1 meg resistor. Okay, so that's going to go in there. Now what I haven't done is powered my thing. So this top one goes into there, this one goes into the bottom. You can easily trigger the sample hold phases by plugging the other end into the positive or negative rail. Okay. Next, connect the circuit's output to a multimeter set to measure voltage. Squeeze that in there. DC voltage. So I can do this by... let's take a different colour. So the output, I'm assuming, is going to be this other socket. So if I take this and sleeve with that one, let's put this in there, you can see it. So I'm attaching the negative to the sleeve and then a positive to the end. Okay, we've got a nothing at the minute. You can't see that. Sort it out. Get this in place. Come on. So next, connect the circuit's output to a multimeter, set it to DC voltage. Plug the jumper into the positive rail. Naff all happens. This will cause the circuit to enter the sampling phase, meaning the voltage at the capacitor starts following the input voltage. Then plug the jumper into the negative rail, which will turn it to shut off. I've got some serious droop. What? So, all right, that's... there's some serious doubt going on here. I've got the envelope going through. Yes. I plug it into the positive rail. Yeah, I don't know what's going on, but it's not quite working. So I'm going to have to go back through this, I think. See what the heck and all any of this is about. And I'll probably spot something which is completely missing. That's what usually happens. Not seeing it right now. Oh, I can see part of it. I can see part of the problem. Right, okay. Let's try this again. This here is not in the right hole. Okay, good. Has something worth changing. Let's try that out. Okay, got all sorts of voltage coming out of there now. So, if I plug it into positive, still just plummets, doesn't it? Really interestingly. I plug it into negative. That should hold it, which it does. Alright, if I plug it into positive again, it's not really changing. It's just dropping. Plug that into negative. Yeah, alright, well it's still not quite working in any way, shape or form. Oh. So to be sampled signals going in there. There's nothing on that back end, just so it's there. There's nothing on the front signal. Just got the signal out the back. Yeah, the one at the back and the earth at the front. Yeah, that makes sense. Get every different voltage every time you switch phases. We've got to at the very least get this right, haven't we? We've got to at least get this right. So that's looping. I can make it loop slower. Does that make any difference? That is going into here. That's plugged into there. So when this is plugged into positive, which is that side, I should be measuring something. But all I get is dropping voltage. And that's not as if it's going up and down. Alright, so let me take that out of there. Let's measure this to start with, just to see whether I've got bits of theory right, yeah? So look, positive and to negative voltage, that's coming out of that envelope. So I know I've got a signal coming out of there, and I'm measuring it correctly on the end of the cable. So that much seems to be correct. Now I'm plugging it onto this cable. I have a voltage which then falls. This is a point voltage. This is a very small voltage. It's currently in positive. So I put it into negative. It should hold a voltage, which it sort of does, but it's the same one every time, more or less. Can you see that? Put this back over here onto this side. It just gradually falls away. Put it back into positive. And it goes back to that other voltage. So something is amiss. So let's have a look through, because if nothing else I want to get just a simple bit of sampling working. That has to work, doesn't it? Has to work. So let's go through. Wait to see if it goes back up. I suppose, but it's not anywhere near going anything like the speed of the envelope. So let me check. Let's check through first, see what we get to. It's bound to be something I've got wrong here. So bring this back in. So check this. So that's in. The earth is going to ground. Back end, which is that, is in. It's going to 2 below, yeah, and then that's taken another cable here all the way over there. Now it's possible that that cable's not really in because it's sort of not quite long enough. Maybe I should get something longer. That's way too long. Let's get let's take this out of there. And this grey one goes on the end and then ploughs in to that right hand leg. Okay, messed that up. There's a resistor in the way. Right hand leg. Okay. So pin 4, 1, 2, 3, 4 has to be going to negative. Pin 4 at the top is going to positive. Diode. Oh, is that even the right way around? Yeah, good lord, it is the right way around. That's going into that pin right next, front end of that. That is connected to it. Over here I've got pin 1 and 2 connected to each other with a cable. Then I've got this Mr. JFET sitting in here, 1, 2, 3, with the middle one going to our 100 nano capacitor. And that is actually a leg too far over, but it's only connecting to that one that's going to there, which is actually right. But maybe that is still right. All of that is right. That comes to the other side of that. Okay, let me bring this in so it's as accurate as possible. That's going to that one. It doesn't go. That goes to that one leg, which is middle leg completely missing. Middle leg, that to that one, yeah. Okay, that is straight to there. That side going to ground, which makes sense. I've got this cable just next to it on 25, yeah, going to the other side. And there I've got my 1K resistor going to the back end of that front end is going through to ground. Yeah, I mean the wiring is looking good at the minute. I mean, I've made a couple of adjustments that perhaps might do something. That grey cable there is going from pin 3, 1, 2, 3, yeah, to the first leg of that, yeah, first leg of that, which is going to the middle of the JFET, which it is. That's all right. This side there's only that, and there's that going to ground. That's going to ground. That's going to negative. That's going to ground. Do I have the tiny jumper next to the 1 meg? Yes, I do. I do. The 1 meg does jump over a thing. The 1 meg goes from the left pin to the right pin, same with the JFET. Okay, well let's connect it up again, see what, if anything, if that has done. Let's have a look. So this is this end, plugs that in. Take the purple cable, plug that in there. Take the output from there. Maybe I stick it on my tongue or something. Put this to DC voltage. Put this on the shield. This on the end. Okay, it's better. Look at that, it's moving about. That's surely what we want, isn't it? Oh my goodness. So when I put this into positive, it should start the sample. I don't know. Shouldn't it then grab a single value? I don't know. And then when I put it over here, it should hold a value. Okay, 1.1. Let's try that again. Plug it over here. .35. I mean, do I actually need to put it over the other side? It's just moving 2.99. 2.44. There you go. So I think we got that working. I think we did. So there was obviously a wobbly something or other in there that wasn't quite right, and you just have to go through it and persevere. Flipping persevere. That's the idea. Whew. Right. So our little circuit is working. We are triggering it, and it's doing its business. Oh, sorry, that was on the completely wrong thing the entire time. I'm sorry about that. Let's go back to the manual. But you saw that happening, yeah? Let's put that back to, sorry, put that back to the overhead. You saw that happening. Let me do that even on the little screen. So if I unplug that, it then motors around the place. When I plug it in, it takes the sample. So it's sampling, it's sampling, it's sampling, takes a sample. I don't know why I need to plug it into positive. That doesn't seem to do anything. Maybe that enables it to start with. I do not know. But I guess the fact that I'm having to do this long switch is neither here nor there. But every time I plug it back into negative, when it's potentially turning it off, it selects and holds that different voltage. Yeah, see, got it? Good, excellent, excellent, excellent. Back to the manual then for the minute. So, that craziness. So you should get a different voltage each time you switch, yes. So operating it manually is not what we want. So let's try to automate it. Use a regular square wave LFO, that's what I would do. But that signal will probably not be beefy enough. Okay, so sampling phase, we need to push the diode shut with enough force. That's interesting. For the hold phase, we need to pull the voltage below into negatives as far as possible. So what we'll have to do is take a square wave and blow it up. Now, I wonder what we can blow things up with. Maybe it's an op-amp. Yeah, an op-amp based comparator. Comparator does just what the name implies. It compares an input voltage to a threshold voltage. Whenever the input is above the threshold, it raises its output to the positive voltage, and vice versa. So what do we want the threshold to be? Because we don't want our comparator to fire randomly, if we leave the input unconnected, which can happen with interference, and push it above the 0 line. Sorry, we don't want that to happen, which is why we can't just have it at 0. By using a voltage divider set to a 3 volt threshold, we can make our circuit interference proof. Only downside being that our input square wave has to be at least 6 volts peak to peak to trigger it. The second problem, instead of nice distinct steps, we get these strange angled monstrosities. I don't know, I don't think they're so bad. What's up with that? Well, since we're using a square wave, sampling phase is exactly as long as the hold phase. As we know, during the sampling phase, the output voltage will follow the input voltage. That's why we get these angled parts in our output. Okay, that's why this was moving about in between. That's why it's moving about now, because it's just following the input. It's only when we turn it on, does it, that's the wrong thing, does it stop? So we want it just to momentarily go bip and then stop again, bip and stop again, bip and stop again. That's my thinking anyway. So to do it, we need a simple high-pass filter. Okay. And it's really only a capacitor followed by a resistor. Why don't we just have, rather than a square wave, why don't we turn it into a quick pulse? Would be what I just did, I guess. But okay, but instead of that, they're using a high-pass filter, which is a capacitor followed by a resistor to ground. This will convert the square wave into voltage spikes. There we go. It converts it into like a pulse. To make them short and snappy, using a super small capacitor and a big resistor. Next, we need to get rid of the negative spike. Well, then we can use diode. Yes, followed by a 100k resistor. This way, only our positive spike comes through. Brilliant. Okay, let's give this a try. See all of that on there? So we've got a couple of changes to make. Let's see if I can get this right first time. So let's take out our bit of battery, unplug that, unplug that for the minute. Right, what have we got to do? Oh, where are my glasses? Let's put it back to overhead. Right. So my op-amp stays in the same place. This stays the same. This is doing that, doing that thing. All of that looks very similar. That's the same, that's the same. What are we trying to do? We're replacing what's this bit. Essentially, we're replacing this trigger here with something a lot cleverer. Yoink, let's get rid of that. First thing we need is a little tiny thing, because we're using an op amp, so we're going to use the end of the op amp on that top pin there into our diode. I may sneeze. Oh, excuse me. So diode, pin 1, stuff that in there. Great. We need another socket, which is the same as this one, but down the bottom, so about there. Oops. That's cool, that's lining up with that earth to ground bit there. Looks like we need a cable going from the back to one in front. Okay, good. Need a 100k resistor, 10k. Those all the 100ks? Could be. That was 1k, wasn't it? It's 10k. Pretty sure 100k is the big load of 12s. Let's go and have a look. 100k is a bag of 12s, yeah. So 100k goes from there to ground, pin 24, to ground. And I need a 1 nano capacitor. Did I mean the 1 micro? Nano farad. Page 22. So 1 nano. I don't have any of those. Not as a foil. I've got 1 ceramic. It'll have to be that. Which is this one, the 102. Yeah, okay. Oh no, don't do that, don't do that. Flipping auto something or other. Okay, so 1 nano has to go to the end of the 100k and then to that one in front. End of the 100k to that one in front. Can't be right, that's on 24. This must all be further away than it needs to be. It goes to the one in front. To the 100k, that's the one in front. To the 100k. The other diode goes from pin 3, front end, also to this 100k. 1, 2, 3. And there's another 100k. Goes from the end of that to ground. It's creating a bit of a divider, isn't it? Comparator, as it says. Yeah. That's next to that one, which is going to positive. Then I want a nice long cable going from next to that 100, pin 2, all the way over here somewhere to 8, like that. There's a 33k and another 100k. Thanks, Romeo. Yeah. 33k goes to ground. This is next door. $100k goes to positive. There's a couple of weenie ones. Connect that to the 33. And that to there. Is that everything? Got one there. This circuit going to there, that going round. That ceramic in the way. Any other changes down here? That's going straight through. That's to the back, that's to the back, that's the one in front. Okay. I kind of forget what I was trying to achieve. Tanuki, no, there's two more modules. There's a wave folder and an output module. So this is module number 7. This is video session number 8, because we also built the power supply and case as one. So there's still more to come. So what do we do once we've done all of this is the question. I think I've covered all that. Because we've now got a second one of these. What's that for? So if we send a square wave oscillation to the trigger input while connecting the circuit's output to a VCO's CV input, we should hear the pitch go up and down in obvious distinct steps. But what if we don't have a square wave LFO to hand? Because I don't. No worries. Since our module should have an internal clock anyways, we'll take a slight detour and set one up now. Okay, can I remedy this? I mean, I can take a square wave out of the VCO. I didn't think to set anything like that up. 1 second. Let me think. I mean, sod it, I could bring in an LFO, couldn't I? Just give us a minute. Talk amongst yourselves. An automatic jumper wire inserter, yeah. That's right. So, it's the easiest way to do this. Let me turn on my machine over here. Is it still plugged in? It is. So let's have a look. There's Batumi. Square. I've got saw. I don't have a square out of here, do I? Yes, I do. The bottom one. Right. Up and down. Up and down. Right. Okay. So the input seemed to be this left. Oh, it's a bit not quite right. On there. I've now got two things. What do I want the two things for? Okay. I wish Moritz would label the ports on these breadboards. That would be very useful. Now, before I use this one, so what's this extra one? But let me get an output working first, because that's going to become important. That's not long enough. Okay, so that works. So we've got some sound. Now let's try to follow the instructions. So send a square wave oscillation to the trigger input. This is our trigger input. We think. Because that's what we use. No, that's not our trigger input. That is the source. So we're not putting a square wave into that. So that is wrong. We want to put it into the trigger input, which is this. This is the trigger, because that's where our piece of wire was. So let's stick that into there. Let's power our circuit. Lovely. Let's shift that out of the way. Is that worse? Better or worse? Okay, square wave into the trigger input while connecting the circuit's output to a VCO CV input. So this is the output. But what's in the input at this point? CV input. So I've got nothing being sampled in here. So presumably, do I take my envelope, plug that in right before? Ooh. Right, that seems to be working. Sorry, was that loud? I do apologise. Sort of. So we have the envelope going in, which is creating like an LFO of some kind, a slowly moving waveform. That is being sampled according to the trigger from the LFO over there, which is triggering this. And the output is generating a bunch of stepped voltages, which have been sampling the envelope, which gives us the rise and fall of that. Now that's pretty good. I mean, we are 2 hours in. You know, 3 hours feels too long. We've got, you know, maybe we can keep going for another half an hour and to see how further we can get. So it would be nice to look at the noise circuit, but we do have, this is sampling and holding. It really is. We're triggering it with a square wave. It's sampling and holding. I can speed that up. By changing the rate of the LFO, I can change this. Which gives it, it's moving faster, so the values are not quite so distinct. As I make it slower, you get that up and that down. That's great. Oh heck, sorry, I wasn't watching. Sorry. I don't have time for high definition nudes right now. Apologies. And anyone who isn't looking on YouTube, of course, has no idea what I mean. It's just that we get these occasional crazies who come in offering us sex, which is nice, obviously, but we're doing something else at the minute. We don't have time for that. So your best adult dating site is just going to have to be blocked. So, you know, come back when you've got something nice to say. Right. Okay, so we've accomplished our sampling and holding. Now, it does say here that what does it say? That if we don't have an LFO, we can set one up. So what I think I might do, so the clock generator, that's the next part. I might skip that if nobody minds. I think we get that. Well, no, we don't. I mean, it will be nice to learn about it, but we have to sort of decide what it is we're going to tackle. Well, I don't know. It does look quite interesting. Let's just skip through for a minute. Buffered adjustable input and slew output. Wow. So the slew output, okay, well this is interesting. Let's just read through this for a second. So the slew output means having it glide to varying degrees between consecutive voltages. So the advantage of this, I suppose, is that so we no longer have a stepped output. We have we're almost a continuously varying output because it moves from one to another. Does that make sense? Well, it is really getting busy in there. So yeah, what I think we'll do, I mean, obviously if you're doing this at home, then you know, go through the whole lot. That's fine, because the place that we've got to is that what they want to do is add a clock to this, so it has its own clock rather than having to bring an LFO in, which sounds brilliant. Then they're adding slew so that you can smooth out the steppiness of sample and hold, although I personally am a fan of the steppiness of sample and hold. to give a smoother randomization output, and we'll see that when we solder it together, because that's what one of the outputs that we'll get. So that, I think, is what this is all about. So let's see if we can tackle the noise generator in this last bit, because I think that would be worthwhile. Let's just see how many pages it is. Yeah, no, it looks good, looks simple. Let's do that. Let's do that. I think that's a good idea. I'm going to elect to do that. Let's take this out for the minute. We'll be dismantling this anyway by the looks of things. So back to the manual then, on noise basics. From a physics standpoint, there's actually no distinction between noise and any other sound. They are by definition just vibrations in a medium. We are all stardust. So when dealing with synthesizers, you often hear people talk about coloured noise, white noise, red noise, pink noise, so on. Type of noise we're interested in here is what distinguishes coloured noise from any other type of sound? To start off, let's looking at what is usually referred to as white noise. White noise is a noise that occupies the full range of audible frequencies. So the x-axis shows frequency, the y shows amplitude. As you can see, every frequency is present here. Yes, in your little drawing, I can see every single frequency. Let's get out of the way. Don't do that. So let's contrast this to a spectrogram of a sine wave. Yes, a single frequency. There we go. So basically, sine waves and white noise couldn't be more different. Yes. White noise is chaotic, unpredictable mess. This leads us to a more useful description of what our ears perceive as noisy. Randomness. The more random and unpredictable a sound is, the more noisy it's going to seem to us. Now, in the world of electronics, sound is encoded as fluctuations in voltage over time. So if you want to build a circuit that generates white noise, you essentially have to build a circuit that generates a randomly fluctuating voltage. Yeah, that makes sense. We do this by abusing a transistor. So the deal with semiconductors is that they only allow current to flow under certain conditions. For NPN transistors, no current can flow into the collector as long as there is no current flowing into the base, at least in theory, because you have to turn it on at the base and then current flows. In practice, if we check the data sheet, we'll find multiple mentions of something called a breakdown voltage. There's one specified for each of the paths between collector and emitter, collector and base, and emitter and base. So a small voltage, regular flow. No voltage, collector base breakdown. Okay. Alright, so it just means that you can only push a transistor so far before it starts misbehaving. If we apply more than 30 volts between collector and emitter, transistor will start to conduct even when it normally shouldn't. You can kind of force things through. Same idea for the path between the emitter and base. Under normal conditions, current should not be able to flow, but if we stick in 6 volts, then it will break. How does this help us? Well, as is often the case, things are not as clean-cut as you assume. A transistor breaking down doesn't mean the floodgates simply open up and the current can pass through unobstructed. In reality, something weirder happens. We see random, smallest bursts of current flow through the transistor, random in timing and intensity. As if it's still fighting not to break down but can't quite keep up. This is what we want. So to actually make noise happen, we only need 2 components, a transistor and a resistor. Here's how it works. Connect our transistor's emitter, that's the arrow one, to the positive supply through a resistor. Then we ground the base, leaving the collector unconnected. The resistor serves one purpose here. We need to convert fluctuations in current to fluctuations in voltage. So why does that help us with this? To understand that, let's first assume we've dialed our supply voltage down below a 6 volt threshold. Now, no current flows into the transistor's emitter because the transistor is not breaking down yet. It means that the pushing force, which is what voltage is, does not actually push any current through the resistor. So the voltage at the emitter is the same as it is above the resistor. Okay, because no pushing's going on. So as we increase the voltage significantly above the 6 volt threshold, the transistor will begin to break down, resulting in random bursts of current flow through the resistor into the emitter and out of the base. See, that arrow's annoying me. Now the more current flows through the resistor, the more the voltage at the emitter will drop. That's because the pushing force is allowed to transform into actual movement of electricity. Oh, it all goes scary. This way we convert the random fluctuations in current flow into voltage that drops below a set supply voltage in random amounts and random intervals. Great! Though if you'd set this up and tried it, you probably wouldn't hear much because the output signal is really low. So we should probably amplify it. Well, what with? An op-amp? Let's do that. Doesn't work in the circuit simulator. Before you can do that, you have to center the signal, because an amplifier needs enough headroom to be able to work properly. We'll use an op-amp here. Because we're amplifying a waveform basically means stretching it along the y-axis. It should be clear why we need more headroom. Yeah. So we center it, we'll route it through a high-pass filter. As the high pass only allows frequencies above its cutoff to pass through, it will remove the constant positive offset of our signal. High pass, yes. So it cuts out anything which is a constant, yes. Now, since we want to remove as little of our noise as possible, we choose a capacitor resistor combination that gives us a very low cutoff frequency of just 1.6 Hz. We can send our centered signal into the op-amp, which we'll configure as a non-inverting amplifier. This should give us a gain factor of around 150 with this combination of 100k and 680 ohms voltage divider. So we'll blow our noise signal up to around a 10 volt peak to peak. Hey! Recommend we build it on a separate breadboard so we can eventually feed the noise into our sample and hold circuit. Second breadboard? Oh my goodness! Well, I do have two, so heck, let's do it. Let's do this thing. How am I going to power both of them? Let's not worry about that right now. There are other things we could be worrying about. So we've got a second breadboard. Now, if you're using 9 volt batteries, make sure to connect the transistor's base to the negative rail instead of ground. Okay. Well, I'll just do what it says. Why do I have to make that decision? Alright, don't quite know what to do about that bit yet. So, what I'm going to do is I will mirror the voltage part of this. So that goes in there. This one goes in the top. Go that way around. And I'll plug the batteries directly into there in a minute. In the meantime, all right, yeah, okay. I'm just getting on with what I'm doing, all right? So overhead, let's have a look-see. So we can just sort of push that out of the way for a minute, bring this one in. We're going to need that second op-amp chip. See, I told you it was a good idea to do this one. This is going to go in one below 15 up to 20, that way round, like so. Going to stick a blue one to positive on pin 4. I need my glasses. Two, 3, 4. And down to negative on this side on the same row. 2, 3, 4. We need another 100k. 2 of these, 3 of these. 1, 2. Are you all right there, Mark? Have you just come to fill us in on your exploits? Right, so 100k goes on that third pin down to ground. 100k, third pin down to ground. Got another one going between the last 2 pins down the bottom here. And one more, pin 6 to positive. Okay, need one of these. Goes in alongside, about there. And that takes, I'm doing this completely out of order, I think. Let's go into, where's me what's it? Let's go into ground. There to there. Yeah. We've got something crossing over from that 100k over the top. Woo! Crazy. Now we need the BC transistor. CTBC is one choice. That's a 3904. So I think it's this one then. CTBC. We talked about transistors. NPN. The BC 458. 458, yeah. So it goes that way around. One pin onto there. 1, 2, 3. And I've got a line going to, I think, negative, although it's a bit unclear. I think it goes to negative, the middle one. Come on. Okay, good. One micro. Okay, we'll get to that. 680. It's this old brown thing. Next to that. And where does it go? Just to ground. I've got a little line. It's jumping from pin 1 to the back of that. Like so. I've got a line. Jump in the middle. I've got a 1K. Thanks, Mr. Wiggly. Who's designing kick drums? Am I generating something that I'm not aware of? Yeah, that's always possible. Oh, geez, come on. We can do this. It's nearly 10 o'clock. We could do it. We can get noise. We can generate noise. We can. Is that it? So there's that. That's 100k. That's the thing. That's me 1k to the back of that. Ground's going to that. I don't have all my legs involved in something with that, but I don't need one because one isn't connected. I've still got to get some kind of capacitor into there and then a longer cable along there. So use this green one to go from pin 3 to a pin away from there. Pin 3, which goes to that one, like that. Yeah, more or less. Good, good. So I need a 1 nanofarad something or other. No, it's a microfarad. Alright, back up to here. One microfarad. It's a J63. There should be 2 of. Nope, 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 nope. It's got to be the 680, isn't it? 2 of 1 microfarad J63. This is the 2. They're all the 104s. What am I missing? J63. That's the fella. Do you remember what page I was on? Too far. Come on, here we go. So this one goes on the last leg to there. That should be it. That should be the lot. And allegedly, I should get pink noise. I should get noise out. Burst of static. Okay, so that goes there. So let me plug the battery in. So this end goes at the bottom. This one goes in the middle. This one goes on the inside. This one goes on the outside. So I should get some static out of here. Look at that! Oh, you're doing the kick drums. Gotcha. Look at that, we created noise. That's pretty awesome. Good. So we can now potentially plug that into our other thing in order to use that as our sample and hold source. Can we skip to that bit, or have we got a load more stuff to do? Additional colours. Okay, so all right, let's do this quick because it's useful. So pink noise is just white noise sent through a low pass filter. So you get a different range, or you get a reduced higher range. And blue is the opposite, it goes through a high pass, so you get more higher frequencies and less low frequencies. That's the difference between them. Isn't that exciting? Okay, skip. The shelf filter. Yeah, I don't think we'll do that. I think we're just going to use noise we've just generated in our other circuit, if we can make that happen. Do you think it's going to show us, or do you think we're just going to have to try to work it out? So there's lots of interesting stuff on here on converting white to pink, which is, you know, using a filter. So that's all good, and we could build that in. We're not going to bother just now. And then we build in the high pass filter in order to create blue noise, which is the white to blue converter. Good, we're getting the hang of all of this. And then, oh damn it, it ignores the coming together of these two things. And then you can solder it. Right, so question I have for all you lovely people out there is, how do I share the power supply? How do I share the power supply between these two things? So it doesn't seem to say. So I put this to the overhead. There we go. So I've got these two things now, and I've got one lot of power. Now in my head, all I can think of that just seems to, I mean, I don't know, is I just take a cable from there and plug it in here, right? And take a cable from there and plug it in there, one from there into there, and one from there to there. Is that right? Is that what I do, or is that going to ruin something? Yeah, jump between them, says Ken. Yeah, that's what I think. You know, is that really stupid? So while I find some jumper cables, feel free to jump in and tell me that's really stupid. So I'll get like a red one. There's a red one. Is that going to be far enough? Yeah. Another red one. A couple of black ones. I mean, all I'm wondering is whether it would drop so much voltage it wouldn't work, but is that likely? But then why would it? I mean, that's just showing my complete ignorance of how any of this electronic stuff works. But you know, I'm thinking of it in terms of water flow, because that's how these things are talked about often. So if you divert a load of water from one place to another, you're going to lose some of that pressure, aren't you? Aren't you? Oh, I don't flipping know. So in which case, let's just do that. Let's patch it across, and we're just going to assume that's all going to work beautifully. And then I've got this as an output of noise, which is going to be the thing that's being sampled. So that will go into this input. I haven't built a clock, so I'm still going to need my LFO as my trigger. And then I should get a voltage output into my LFO, into my VCO, which we can then hear. And this is going to be a flipping sample an old circuit using noise and all of these things we have created out of thin air. We have forged them in the power of electronicness. It's flipping amazing. I love this stuff. So, all right, so black to black. So that's going over there. This red one on this line, which is part of the ground, going to that one over there. This, let's go with the red one first. On this end, goes into there, and this black one here goes in there. No smoke. It should all just bloody work then, shouldn't it? Right, so I've got this green cable here. I can plug the output of that into the sampling input. This thing here, which was the Batumi, I can plug into the trigger. This, what was this? This is the output of the oscillator. Sonic USB 1000 watt. Then this pink one. Once I connect this pink one, we can all then have a party and go home. Ready? Somebody let a wasp in. Is there anything to say I couldn't use the step sequencer? The sequencer over here is the clock. In fact, couldn't I just use the clock out? I might try that. I mean, that seems to be working. You know, party. But couldn't I use, just to keep things in the family, the clock out here? In here? See? Or maybe more interestingly, you could take CD out of this. Take this as a filter. You can see what I'm doing, right? Yeah, I'm going to take the output. Into the filter. And take my sample and hold into there. That'll do it. It's just about there. Something's going on. Yeah, that's hard to discern, I would say. So let's put that just straight back into our oscillator. And what am I done? No, I've created a feedback loop. We're all going to die. And this is coming out of here. That goes into there. And this comes out of there into there. So it's definitely happening. It was kind of hard to hear, I think, on the filter because the range isn't very big. So there's probably reasons why the range isn't big, because we haven't built in the something or other to do the something or other thing. You can just about discern it. Good. Well, there we go. I think we did that. I think that's great. Super duper. So there we have it, the noise sample and hold. We created a noise circuit here, and we created a sample and hold circuit up here, and we used the noise as the sound source through which we sampled and obtained a mystically random voltage value. There was something about JFETs in there. There was something about drains and sources, and how when you had your base and your source the same, something happened, and then when you dragged your voltage down through changing the resistance somehow, it then turned off and held that value because of a buffered op amp that we stuck in there. So we did. Yes, we did. So that was going on. Meanwhile, in the noise side of things, we took another transistor and we broke it, and that forced it into random bursts of stuff, which generated white noise out of here, and it's that we sampled through, in the end, the clock from the sequencer over there we did. So yeah, that was a success, I think. That was a success. We like it. Now, there's a lot more in the manual. Pages and pages more about creating different coloured noises, and also there was something else. Oh, you created the clock. We created its own clock internally, so it doesn't have to be clocked externally, and it also created a slew circuit in order to give you a smoother ride with your randomizations. So all of that is built into the module, which we will tackle tomorrow. This fella here. So on the front panel, you've got your rates. It's your clock at the top on the big knob. You've got a slew level, I suppose, and then you've got a slew output, but also a slew input. We didn't really investigate what that was about, but don't worry about that yet. We've got a CV input. What would that be for? Is that the sampling input? I suppose it is. And you've got separate outputs for your noises that you can use elsewhere. Or are you going to be patching that into the CV input? I wonder, is it? It might not be patched internally, in which case you would patch it on itself. Interesting. Interesting. And then you've got your output there. One thing, says Mark, what are you going to tell us about? We sampled, we held, we did. Is there a clock out? Not that I can see, no. Which is a bit of a missed opportunity, I think you could say. It has a clock in, so you can override the clock. Doesn't have a clock out. There's room for one here, look, you could have stuck one there. Maybe I'll stick my own one on. Cool, right, so there we go. Tomorrow night then, same time, 7:30, I'll solder the thing together. Should only take a couple of hours with a bit of luck. Bit of testing, screwing it into here. I think I've decided not to use knurlies on this case anymore. I'm going to try to find a bunch of other regular screws and screw it in, because everything is still a little bit self-tapping, and I'm not sure how healthy that is. So good. I imagine it's going to sit here, which is quite cool. And I hope it can give us a bit more bubbling on our filter, which is what I really want it for, ultimately. So yeah, we're nearly there. Join us tomorrow, 7:30. We'll get on with the soldering. That'll be great, I think. Unplug that from somewhere a bit so it doesn't all drain away. Okay, good. So I'll pull that apart, and tomorrow we'll solder it together, and we'll see how it all works. So thanks ever so much for spending time with me this evening. That was all right. That it was. Yeah, it's yes. I think I retained some of that. I think I understood most of that, which is always good. Yeah. So thanks for that. I hope that's been helpful. See you again tomorrow for the soldering. In the meantime, you know, go make some tunes on that, and I'll see if I can find, on first attempt, my outro. That's good, thanks. Take it easy out there. I'm going to go and have some pudding.